Okay, week 2, recurrent neural networks, EE546. We're going to talk about recurrent neural networks themselves this week. Actually, the general name is recurrent neural networks. However, the recurrent neural network, as we know, of which we are going to describe today, the vanilla recurrent neural network, is not being used today, but it was how it emerged. So we are going to start talking about this. But before we start, I guess a simple history is in order. Kontrol edemiyorum ya. Allah Allah. Okay, so this was my first. Arkadaşlar şey yapamıyorum bilgisayarda. Evet, neden şey yapamıyorum? Bakın, okay, so this is it. So we start with a little bit of history. This is the guy who is kind of the godfather of deep learning, they say. Because, you know, Geoffrey Hinton is the godfather of deep learning, but this guy is the first guy who thought that we could connect different layers with nonlinear functions and they would make good decisions. He's got a good paper, group method of data handling. And what he proposed was actually some a graphical computational graph architecture of polynomials. So he obtained a nonlinearity by using higher order polynomials, and they are today referred to as the polynomial neural networks. I mean, there are a lot of guys here, but this is one of the nearest architectures that we have today, as we know, deep learning. It is closer as an architecture. This one is closer to our architectures. Then, following this idea, we had many different ideas as well. Another important thing was between 16th and 70s, the idea of backpropagation was introduced by this guy. It was his thesis or something. No, it was his paper. So first the idea of continuous backpropagation, then in 62 by Dreyfus, more important, the idea of backpropagation in computational graphs. So if you have a computational graph, you could carry the derivative by using the chain rule. That was the idea. Then this guy, which was his master thesis, by the way, he proposed the idea of automatically backpropagating the gradients to train these so-called network architectures, neural networks, for learning a given task. This was the first time it was being introduced. So the thing that you're very accustomed to doing today in deep learning is something of a half century old, which makes it, in my opinion, kind of new. Then other people worked on this idea, applying this to nonlinear functions in modern artificial neural networks in the 80s. And actually, in the 90s, people started talking about backpropagation through time, which we are going to talk about next week, because backpropagation in the computational graph, you know what it is. You learned it in your prerequisite course, either in convolutional neural networks or artificial neural networks. You had a computational graph, and in the end, there's a gradient which was constructed by a cost function or a loss function. And by backpropagating that gradient in using the chain rule, you updated the parameters, right? So the backpropagation direction was the back direction of the computational graph. However, there's another direction that you could backpropagate derivatives, which is the time or the sequence dimension, which is an important thing for training recurrent neural networks, which was proposed for recurrent neural networks in the 90s, and we are going to talk about it as well. Okay, so these ideas are very new, but there is something I also want to talk about. Around 1980s, these multilayer perceptrons were studied. They were frequently pronounced in papers, but the academic society lost faith in using them. And actually, if you look at the number of academic studies around that time, this is a graph I've taken from this History of AI Winters by Milton Lin. It's a blog, visit it. the number of papers around this era just fell down. Today, that era is called the AI winter 1, because we've got another one. Because people have lost faith in that kind of studies. Then by the end of the 80s, the studies started to emerge again. Then there was another winter in the 90s. Then after 2020s and after AlexNet, there was exponential growth. Why am I telling you? Because you most of the time hear people talking about this deep learning being a hype, or deep learning being something temporary. Yeah, it's true. I mean, in the history of AI, there were times that people have lost in the idea of training non-transparent architectures to learn tasks. Yes, but those winters have passed, and the ideas came up more strong, and the growth was again exponential. So it is funny that some people in the literature think that the AI winter will come. They're always saying the AI winter is coming. I call them the Starks of the deep learning era. And I know a couple of guys, important guys, some professors, some guy from Italy, for example, they are always writing about this. The next AI winter is coming. But I think that, because they think that, it will lose its momentum, and we're going to be dealing with more transparent architectures soon. I don't believe this, guys. I mean, each time an AI winter passed, what I see is we are dealing with more complex architectures and less transparency. So there will be winters that we will have to discuss new ideas, but each time it comes back, it's going to be coming strong. Why am I telling you this? Because I'm working on this field. Most probably I'm going to be working on this field if I live long, many years from now. And if you study this field, I do believe that it's going to come back strong every time. So just keep that in mind. So this was a part of the history. Now I continue. And in 1989, the first idea was how the first AI ended was a key finding by Hornig. Multi-layer feed-forward networks are universal approximators. In his paper, he mathematically proved that if you have multiple layers, it can theoretically learn and implement any function in the entire function space. Okay, so that was an important discovery, because it meant practically, if we could train these networks, we could do anything, it was saying. But the tricky part was how to train them. So we've spent, the scientific society spent the succeeding years trying to find out how to train them. I mean, they have found the ways to train convolutional neural networks using GPUs in 2010, 2012. So that was a revolution. Now we are working on how to train recurrent neural networks better, actually by LSTMs we are going to learn in this course. That was also a revolution to effectively train recurrent neural networks. So the main idea is, since we know that these graph architectures, layered architectures, can learn any function, we are trying to find ways to train them. And actually, in the first part of this course, in which we cover recurrent neural networks, how to train them, LSTMs, types of LSTMs, and what are the architectural details of the variants of LSTMs, we will always be trying to find ways, or we'll always be examining the ways people have found in the literature for this purpose, to train them properly for a given task. Okay, so that's a bit history. So I'm about to finish the history, don't worry. So in the 80s, a special type of RNN, a recurrent neural network, was also introduced. And before recurrent neural networks, there was an idea of a Hopfield network. Actually, maybe when I had it in my when I had a neural networks course in 2001, when I was a master's student, in that course, Uğur Hoca taught us about Hopfield networks. Today, they are so insignificant that most deep learning courses pass them. But Hopfield network was the first idea of an RNN. What is the idea of an RNN? We are going to be talking about this in this lecture today, that the part of the output of the network is being fed as an input, so there's a feedback. But it was a primitive implementation of the idea. However, in 1986, Rumelhart and others introduced the general idea of RNNs, which we know as the vanilla RNN, and which we are going to cover today. And it was an important idea because it was giving the general idea of vanilla RNNs, and it was saying that RNN is different than an ANN, artificial neural network, or FFN, feed-forward neural network, in the sense that a part of the output was fed back to the input to create a memory. So, and also you could create layers out of this network. And frankly, one of the authors of this paper as well was Geoffrey Hinton. Geoffrey Hinton is also the guy who is the supervisor of the paper, which you know as the AlexNet paper, Alex Kirzewski's paper in 2012. So in the cornerstones of this literature, Geoffrey Hinton was there. That's why today he's called the godfather of deep learning, guys. Okay, let's continue. So let's pause history here. We're going to be, well, I think I've decided to stop history in the slides at the point where we introduced the vanilla RNN. Because to continue to understand the history, we have to understand what vanilla RNN is and why it is good and why it is bad. After we understand that, we are going to continue with the advanced structures that followed RNN, and that would be like following the history as well. But for now, we stop here. So let's talk about vanilla RNN. And it's different from a standard feed-forward neural network. So let's again remember what was the feed-forward neural network, or also called artificial neural network, or in deep learning literature today known as the fully connected layer or the dense layer. In the architecture, we have an input layer. So it is a mathematical vector of inputs, and it's connected usually fully to a hidden layer or many hidden layers. When I say connected fully, I mean there are connections from each input node to each input node layer, to each hidden node layer. So there are connections here and here. They are fully connected. They are not necessarily fully connected, but that's the general case. And if it's a layered architecture and if it has multi-depth, then we have the connections, these general fully connected connections, in between the layers up to a decision and output layer, which is the value or the score which you are trying to find. You've seen this architecture. You're familiar with this architecture because in the the course that you have supposedly taken as a prerequisite, either convolutional neural networks or artificial neural networks, this was what you have been dealing with, so, a network architecture. This doesn't have to be a simple network, a serial network, layers connected serially to each other. It can be a, how can I put it, a directed acyclic graph. But in the end, it was a network connected from input to the output with no feedback connections from the output to the previous layers. So it was a directed acyclic graph. That's why we say acyclic, because if there are cycles, they would create feedbacks. So let's continue, because that feedback is important. And in the standard feed-forward neural network, sorry for the voice, they've come, at each node, we introduced a nonlinearity, because in history, in literature, this nonlinearity helped us create surfaces that we desire in our decision space. Remember the first lesson of the CNN course, in which we talked about those decision surfaces in a feature space. In a feature space, if you want to create some non-linear surfaces or non-linear hypersurfaces, you needed nonlinearity in these nodes. And actually, this single node with a nonlinearity was in the literature called the perceptron. because using a perceptron, you could create layers, and using layers, you could create a multi-perceptron network, which is also known as the MLP network. Okay, so let's continue. These are the things that you already know, but I'm trying to give you a background on why RNN is different from an FNN. So this was the FNN. You remember this FNN idea was taken from the neural architectures that we have in our body. And in our body, we had the neural system connected to each other with some axons and dendrites. And the axon, that cell body, the activation takes place here. It was connected to many inputs and we had an output. So that the perceptron was the simple mathematical idea of a neural cell in which we did three operations mainly. Weigh each input with some value, which corresponded to the idea of the thickness of these dendrites. So the electrical current going in will depend on the thickness of some cover, which is called myelin in your cells. It will depend on how much of that current will be transmitted to the cell. So it is like the weight that you multiply. Then you accumulate everything inside and you apply a nonlinear function. So you have another value. So that was the idea. And that was a perfect idea because if you could find the proper weights, you were able to do anything. So that was the biological inspiration for the neural networks. Good. But frankly, it was missing something. The feedback connections. Okay, so FNN was simply a network of weighted inputs summed and actuated by so-called nodes. And the set of nodes, if we had a set of nodes, we called them layers. And many layers were constructed to construct deep neural networks as we know. The output layer of a perceptron, the output of a layer, also called actuation, was the input to the next layer in a multi-layered architecture. Okay, so what is the difference? The difference is, if you have never come across this, I mean, we talk about this in the final week of our previous course, but just to remind you, if you already know, a vanilla RNN is a very similar architecture to a single layer feed-forward neural network. The only difference is some of the output is being fed back as the input. So you just apply inputs, you have an output. Some of the output, or for a recurrent cell, maybe all of the output, is being fed as the input. So when you're feeding the input for the first time, maybe you're feeding these values with some initial values as recurrent values. So you're feeding some of the output to the input. That's what we call feedback is. If you're feeding the output as the input from control theory, if you're an electronics engineer or a mathematician, you know what feedback is. And if you're a computer scientist, maybe you've heard about it. So that was the feedback. The first thing we're going to learn today is how this feedback is mathematically constructed in the so-called vanilla RNN. Okay, let's do it. Okay, so by feedback, we simply mean a connection from the output to the perceptron's own input. So I said we're going to describe what mathematically this feedback is. We're going to write simply the vectors, guys. Okay, so this is the recurrent network, this is the feed-forward neural network. Let's first remember the mathematical functions we have defined for the FNN or FFN. I use them interchangeably, they're just typos, don't worry, but it's either feed-forward neural network or feed-forward neural network. So FNN, FFN, I mean the same thing. So you got an input vector, you got some weights, you got some nodes, and you got the output. So it was simply, you got simply a vector multiplied by x, and for each perceptron, a separate bias added. So in order to reach the output of a single perceptron, you would write a simpler form of this matrix equation in which this Vi is simply a row of this big matrix. I guess you're familiar with this notation. I mean, it's so simple and you've used it and you've seen it. And in our case, this G function is the activation function, whatever it is. And I'm sure you remember these activation functions from the previous course. They could be rectified linear unit, they could be tangent, 10H, hyperbolic tangent, or sigmoid, or some other activation functions, whatever, we don't care. Better nonlinear, not necessarily, but there are some activation functions. This was the standard FFN. Actually, mathematical definition of the vanilla RNN will be quite similar, with some additional vectors and definitions. Okay, let's do it. So guys, to define the vanilla RNN, I'm going to use the same network, same figure, but this time, these nodes, the outputs of these nodes, I'm going to call A, which represents the hidden state vector. The hidden state vector is the guy who is being fed back to the input. Okay? So in a recurrent neural network, instead of the output, I have the hidden states. If I need an output, I'm going to add another layer in the next slide like this. But I'm not yet adding it. I'm going to discuss this first. So this is the vanilla RNN, by the way, guys. I have an input. I have hidden states at the output, each hidden state value being the output of a perceptron. And actually, I'm feeding back these values to the input. So what I'm trying to say is, the input to this network is not of n values, but is of n plus k values, guys. Because the input is both the x and the a. So if there's a matrix representing these connections, it is not of n to something, it is of something n plus k to something. I'm going to show this in the next slide. So as you can see, guys. So let me just get my pen first. Okay, let me just, sorry. Let me get my color. Okay, so let me get my color. Okay, so I'm talking about this part first, and that part is being represented here, guys, without the bias for the sake of simplicity. There is also the bias, but for the sake of simplicity, in this figure, I'm omitting the bias. We are going to add the bias in the next figure, don't worry. For the sake of simplicity, we are doing that. So just be careful, guys. The input to this network is, which means the matrix multiplication is a vector of n plus k, because this guy is n, this guy is k. So that's why the matrix is k times k plus n. So at the output of this vector, I have a k length vector, which is a. So you might ask, what is the first a I calculate? To calculate the first a, I need an a0, right? Traditionally, not necessarily, this first a is a vector of k values of zeros, guys, zeros. This vector being zeros is very important because, in practice, when we cover more complex RNN architectures, you're going to see that this vector is always zero. And it makes sense, actually. Remember previous week's slides when we talked about that cat image being asked to a person. The first answer given was similar to a CNN answering the question. Remember, you show me a cat image, and I say that's a cat image, just like a CNN does. Second time you're asking me the cat image again, I'm giving a strange answer. Okay, cat image again, I'm saying something like this. That's why the second time you're asking me the question, remember that slide from the previous week, I have no prejudice about you asking that question. In the second time you're asking, I have some prejudice because you asked that question to me before. I'm thinking that you're kidding with me. But the first time you're asking, I had no prejudice. So that prejudice was like the hidden states we had. And if I don't have any prejudice at the first time you're asking the question, it is like the hidden state being zero. No prejudge. Okay? So that's why in RNNs, practically, the first hidden state is usually zero. Not necessarily, but practically most of the cases. And this is the definition of vanilla RNN, by the way. if you want an output out of a vanilla RNN, it could be an M-layered output or a single-layered output. It doesn't matter. You need an FFN structure connected to it, like the output layer, okay? So it is like the recurrent neural network, the connection with the feedback, outputting the hidden state only, and the FNN, an extra layer giving you the output. So if you need an output, you will need the extra, extra output layer. Okay then, I think we're clear with this part. Any questions about the feedback from the hidden state to the input and this matrix definition? Okay, it's simple, but it is so fundamental that we are going to take this for granted from for the rest of the course. Okay, guys, so I'm going to call this part the core RNN or the vanilla RNN. This is a recurrent neural network itself, but actually what makes it a recurrent neural network is this core part, okay? And at the core part, as you can see, I'm making a definition of a vector from previous to the next, okay? Good. And I'm going to make this multiplication clearer by, and the other part is the output, needless to say. Okay, so I'm going to dismantle this matrix multiplication into two parts by dismantling this weight matrix into two parts first. So as you can see, this is a weight matrix being multiplied by a vector of k plus n or n plus k length. Some part of this matrix is being multiplied by x, another part of the matrix is being multiplied by a, these guys, okay? So I'm going to dismantle that part as VAX and VAA. So this VAA responsible for being multiplied to the previous hidden state, and this WAX responsible for being multiplied with only the input. And mathematically, I can write this as a matrix multiplication with the input vector plus the matrix multiplication with the hidden state, previous hidden state, plus the bias. Now I've added the bias. It was a time. Okay, so I can write it like this, right? So as you can see, I'm defining two different matrices here, which composes this matrix, and I have the vector BA, okay? Which is a vector of k length because I've got 1, 2, k nodes. That's how I dismantle the matrices. Okay, I think this is clear as well. If you have any questions, please do not hesitate to interrupt me, okay? So guys, this was the actual input to my nodes. So the input to my network is k plus n. However, I am calling x as the input because a is actually not a real input. It is a state. It starts with 0, and as I feed information, it is changing and changing. And actually, you might get a mathematical idea of this state if you think about how to feed different input to this network. Imagine I feed an input to it. I get, what I do is I do this multiplication, and in the end of this multiplication, I have a new a. Maybe using that a, I'm calculating an output. Maybe I'm not. It doesn't matter. Maybe I just forget that. It doesn't matter. If I feed another input, let's say x2, I'm not talking about the vector indices, but time indices. Let's consider that this is x. Sorry, where's my mouse? Okay. So this is the first thing I fed was xt0. Then I fed xt1, which is also vector of n. The next time I'm feeding it, this guy will change again, change. So I'm going to be talking about something like a t0, which was all zeros. Then the next one, a t1, which are some values. And as you feed an input, those values are evaluating and changing. Actually, those are my states. And those are my memory. So I'm going to keep this concept of memory with these hidden states. If you've come across any network with states, that could be a hidden Markov model, or if you're into control theory, you're familiar with states. For example, you have some states in some linear systems equation of a control system, first order, second order control system. It is no different than them because it's an iterative function, and each time you feed an input, these states change. They are mathematically are the same category. But in a vanilla RNN, they are simple as this, simple as this. So these states, this memory is being created by these nonlinear activation functions of these nodes, the so-called perceptrons. Okay, so good. So this will be the recurrent. So I think this is a necessary diagram, but I believe that, as I've written in the slides, is a confusing diagram because it shows almost every connection and every multiplication that exists in a vanilla RNN. Usually when you just come across some vanilla RNN diagrams or RNN figures, not all these connections are being shown. But you don't have to, but you need to understand them. Because if you don't understand these connections, these matrix multiplications won't make any sense to you. And actually, in this course or in any paper you find in the literature or in some blogs or in the books, in the literature, this will not be the diagrams you come across. The diagrams that you come across defining a vanilla RNN will be more simpler, not showing all the connections, but showing different connections between CNNs or RNNs or other architectures. So let's try to get to those architectures slowly. I'm going to be using, so this is a horizontal in this notification. As you can see, the input is here, which is vertical. I'm feeding it to a vertical layer. Then I have this output in between, hidden states in between, and I've got the output. I'm going to change my notation from now on to the one that Andrew Ng uses in Coursera, if you've seen it, in which guys, it will be like this will be an RNN layer, and the input will be fed here, and I'm going to be getting the values here. I'm going to change this one as well. So I'm going to be rotating this 90 degrees in a counterclockwise direction. So don't get confused. I'm explaining this to you because I don't want to lose you. Don't get confused because these connections are very simple. But when you understand them, you can manipulate anything. You can even propose a new variant of LSTM if you totally understand these connections. They are simple, okay? So from now on the following slides, I'm going to be rotating this notation counterclockwise. Okay, so let's do it. Let's do it. So as you can see, I'm going to be define this vanilla RNN like this. So there will be inputs, there will be the hidden outputs. I'm going to use a single square and a circle to indicate all the nodes here. Okay, so it will be a single supernode representation to represent all these nodes. So this representation is equivalent to this representation in which I get the X and A. And a couple of slides later, I'm going to put A here, and the A will flow in a horizontal direction. X will be fed in a vertical direction from bottom to up. Okay, so good. So let's remember our calculations now. Don't get lost. We have the input of some time instant. It could be the first input, it could be the second input, or depending on my sequence length, it could be any input in my sequence. So guys, be careful. My input is of n length, of vector is of length n, as you can see, n. However, the sequence length, I don't know. Maybe this sequence is from T0 to Ts. In that case, I have S plus 1 elements in my sequence. So it's S plus 1 times n data it would have been. But it's important that n is my feature dimension, S is my sequence dimension. And each time I'm feeding an input, I'm getting a single n vector from my sequence dimension, a single instance of my sequence dimension, and I'm feeding it. It's like ti instant being fed, and I'm taking the ti plus 1 hidden states using the ti hidden states being fed backwards. So that's the idea, guys. So if you remember these formulas, that's how we are going to feed the sequence. Now I stop and ask my question. Any problems with feeding a sequence input of n vectors, n values, vectoral, n length vectoral input of x to this recurrent neural network and getting hidden states? Any problem with this definition? I guess not. Okay, it's clear then. Now, guys, the important thing about RNNs, you have to understand this. The first time, I'm going to just draw something. I love doing it, so I'm going to draw a rectangle here. So I'm going to hide this part. So the first time you're calling it, you're feeding the first input of the sequence, which is a vector of length n. N could be 1 or it could be something, doesn't matter. And the first hidden state, most probably being 0, is also being fed. And I'm obtaining this. And I have this. The second element of the sequence is x1, t1. And I'm feeding it, and I'm getting it. And I'm getting another input. And if the sequence is of s length, starting from 1 to s, I'm calling this network s times, guys. So actually an RNN is a feed-forward neural network unrolled in time. Be careful, guys. I was feedbacking my input, right? But in this notation, there is no feedback. I'm feeding the next hidden state to myself, which is another instance of myself. So in this notation, this recurrent neural network looks like a deep FFM because there is no feedback. Actually, there is feedback. I'm using a notation showing it as if there is no feedback. Since this is the hidden state that is being fed back, there is feedback. But I'm writing the nodes, the super nodes, such that actually this feedback creates an RNN, which looks like an FNN when the RNN is unrolled in time. So you unroll it because it's like rolled, but when you unroll it, it is like a deep layer network connected to each other. But frankly, something frank about this network is, okay, that's a layer, this is a layer, that's a layer. They are connected to each other. And each layer gets a total input or concatenated input of this A and X sector. Okay, good, which is n plus k. But the funny thing about this network is each layer has the same weights. You have never seen something like this. You have seen many networks. You have seen VGG, AlexNet, UNets. You have seen ExceptionNet. You've never come across such a thing. Each layer having the same weight. It is very strange. And it's going to be more strange when you try to train this network, guys. But keep in mind that when RNN is unrolled in time, it is actually a deep FFN network, a deep ANN, a deep fully connected network, which has the same weights at each layer. So I guess this is something to digest. And I'm going to ask again, do you have any questions? Good. Well, I continue, but if you have questions, please do not hesitate to interrupt me. So I know in the previous course we have discussed this. This is not the first time you're coming across this idea. Maybe you are, if you have taken my course, or if you don't remember that course, that lecture, I don't know. But most probably, this is not the first time you're coming across this idea. RNN, when unrolled in time, being a deep neural network, which has the same weights at each layer. Okay, we are going to explore this idea to understand what RNNs really are, and it will make us understand the problems with RNN as well, because this creates big problem when we try to train them. Good. By the way, up to now, we have been talking about the outputs, because if you remember the previous slides, output was an additional layer we add, right? I told you that this part was the recurrent neural network. This part was the output, and I have taken only this part and just rotated it counterclockwise 90 degrees to use this supernode representation, and I've unrolled this supernode representation only. However, you can add the output node as well, because if you have the output node, you have the output node for each one as well. Again, each output node having the same weight at each layer in this unrolled representation. So, which brings us to the point, for each input and for each hidden state, we get an output. And in the next state, even the input is the same, since the hidden state is most probably different, we'll get another output, which is again a manifestation of the memory. This is the same way, guys, asking the person, is this a cat image question? Or what is this image question? Imagine the input is always the cat image. Each time the output will be different because the hidden states, because of the weights being most probably non-zero, is going to change the output. That's why when first time I asked, I'm saying, okay, that's a cat image. The next time I said, it was a cat image, it's the same image. I'm not asking for, I'm giving strange questions. That is the mathematical explanation of why we get different answers. So when we said in this slide, mathematically, I'm going back, mathematically mean, it is simply what it mathematically means, guys. And actually, that feedback connection in mathematics, in control theory, most of you electronics guys, you are used to this from control engineering, because in control engineering, we could create many complex feedbacks. I mean, we could put a system to that feedback to control our system, right? A PID controller or whatever. But in recurrent neural networks in this course, it will stay simple as this, because we don't want to change it. What we are interested in this course is to find these weights so that it will provide us with the desired task which we are designing this network to do. Okay, so the network connections, the feedbacks, will not be more complex, but the architectures will vary. And we are going to talk about how the architecture of today's RNNs evolved from this so-called vanilla RNN. Okay then. I think that's, actually we could give a break if you don't have any questions. Cool then.